Good morning, everyone. After our lovely midterm there yesterday, we are now moving away from vectors and bringing our way into calculus. So the first couple of slides here, you don't have to copy them down. I'm just going to kind of do a quick overview of some different things here, and then we'll hit the note part and kind of go from there, okay? So there's kind of two areas of calculus, or two branches of calculus. The first one is control with rates of change. So you may recall in advanced functions, you would have spent some time on the idea of average rates of change and instantaneous rates of change. Okay, so differential calculus is basically concerned with this. How do I find rates of change of different functions and calculate them efficiently? Okay, the other branch of calculus is what's known as integral calculus, and this is concerned with finding the area under a curve. Okay, the two things are actually connected to each other, and we're not going to get into any detail here, but they do have a relationship between the two different types. Okay, and we are focusing on this one. Okay, so in this course, we're doing differential calculus. As I think I mentioned before, integral calculus, if you're taking a first year calculus course at university, that's when you'll start to get into that. Okay. So there's a lot of history. Okay, you can read up on things like, Sir Isaac Newton and Leibniz and arguments they had about who discovered it. It's kind of interesting. There's also a handful of boy band songs about calculus. Okay, and I have no idea if that actually recorded that sound or not. If it did, that's great. If not, you can see here it says Together Calculus. This was a made-up boy band on MTV, kind of back when I was in high school. So check it out for a terrible, terrible pop song if you're interested sometime. Okay. So again, these next couple slides, you don't have to copy them down. But here's kind of the basic idea. Here's our classic equation of a line, and no, I'm not going to draw vectors on there. But what if I want to know the slope of this line, right, or the rate of change that's represented in this situation? Okay, so we know already that rate of change, okay, is basically slope, right? If I want to know the rate of change in a relationship, I have the graph, I can figure that out by calculating slope. So in this case, right, I can just take a little segment here, right, figure out my run, which is 2 units, figure out my rise, which is 1 unit, and oh hey, my slope is a half, so the rate of change between x and y is 1/2, and that's pretty much it. Okay, so that's all fine and dandy with a line. Okay, but what happens when I have this? Okay, I have a parabola. Now I don't have a nice smooth surface. So how do I calculate rate of change? Something like this. Okay, and there's two ways you would have talked about this in advanced functions. Okay, one way is what's called the average rate of change. As well, maybe I still pick an interval. If I start here, and maybe say I end there, okay, I can draw a line between those 2 points and just do the slope here. So when I go over 2, I go up 1, 2, 3, 4. So my average rate of change in that section is 4/2, which is 2. Okay, so my average slope for that section is 2. Okay, but what if I don't want an average? What if I want it at a particular moment in time? Okay, so visually, how we can do this, okay, is to draw what's called a tangent line. And again, you may have done this in one of your science classes, especially again, maybe in physics or something. Okay, if I want to get the slope at a particular location, okay, what I do is I just try to draw a line that just barely grazes the edge of the curve. Okay, and I know I haven't done the greatest job there with it, but if I say talking about this point right here, okay, I've drawn a line that just barely touches the curve there. It's only touching it in one spot. And now I could try to figure out the slope of this. Okay, I'd be making an approximation. Okay, I'm over 1. It looks like I'm up 1, 2, 2.5. So it looks like my rate of change is going to be 2.5 over 1, which going back out to a fraction is 5/2. Okay, but that's the idea, right? Is that if I have a curve, I can draw a line that goes or kind of runs against it, and that will be my rate of change. Okay, and part of the reason this works, I'm going to switch over to Desmos for a second here. Okay, and I'm just going to help myself, I'm zeroing in on a point here. Even though this is a curve, right? If I zoom in a lot, okay, like I'm really zoomed in now, it pretty much looks like a line. Okay, right? So even though the function is curved when I draw it on the surface, over very tiny intervals, it essentially behaves like a line. So if I draw a line that is pretty much parallel to this, right, just barely grazes the surface, that means I'm going to get a pretty good idea of what's going on in my curve in that location. Okay, so that's what we're going to be looking at. So it's going to take the ideas from advanced functions and then run with them with a whole bunch of other things that we can do with it. All right, so this is where the note part actually starts. Okay, so rates of change. And I invite whoever is running this video to just please pause as appropriate to make sure everyone has a chance to get things down. Okay, so we're just going to start with some definitions. So this will be some review for you. Okay, a rate of change is a measure of how quickly one quantity changes with respect to, so that's another one of those short forms. Okay, and I don't know, you may have seen that in science. This is with respect to. Okay, that's what short form is. Okay, so rate of change is how does one thing change with respect to another. The average rate of change is measured over an interval, be it on a graph or something to do with a function. Okay, but it's over an interval, it's the average rate of change. Okay, the instantaneous rate of change is measured at a particular instant or moment. Okay, so not over a length of time, just at a certain time, just at that instant. Again, you would have talked about those two things in advanced functions. Okay, visually, what this looks like, and this is what we're kind of focusing on today, okay, is that the average rate of change is what's called a secant line passing between 2 points, and the instantaneous rate of change is what we call the tangent line running between 2 points. Okay, so again, if I was to do a rough sketch of some kind of a curve, okay, maybe I've got some basic cubic function here. So a secant line, right, runs between 2 points, maybe here and here. Okay, so it's going over an interval. Okay, a tangent line just barely grazes the outside of the function. And again, I'm missing terribly here. Try that one more time. It's a little better. Okay, so tangent line just barely grazes. It's just touching at a single point, and so that's at an instant in time. So we're going to do one example. Again, we're just focusing kind of on the graphical aspect here. So here's the question. A ball is dropped from the top of the CN Tower. Its height above the ground is recorded as it falls. So here's the distances over time. So we're going to graph the relationship and plot a curve to go with it. We're going to do the average rate of change over the first 6 seconds. Okay. And we're going to do a tangent line to approximate the instantaneous rate of change at 5 seconds. So again, especially here, I invite maybe to pause the video, take some time to set up a graph. There should be graph paper on one of the side shelves in my classroom or in the top of the filing cabinet at the back if you need some. So have a look around and see if you can get some if you need some. Okay. But yeah, I'm gonna in a moment I'm gonna put the plot of that graph up on the screen. All right. So hopefully you can take some time to make this graph. Okay, so I cheated a bit because I have the computer, but I used Desmos, and this is what my points look like. Okay. So now let's add a curve. Unfortunately, on the computer, this is not going to be the smoothest for me, but we'll try. Okay, not bad. Try one more time. One more. So that's what the curve kind of looks like, right? It's a parabola. Okay, this is quadratic because it's force of gravity pulling something down. Okay, so the first part was the average rate of change for the first 6 seconds. Again, so on my graph, okay, what that would be is the secant line. So I'm starting at 0. And going to first 6 seconds. Now, we could try to read the slope off the graph here, but thankfully we know the points already. So we can just go to our trusty old friend, the slope formula, instead. Okay, so for B, okay, for the average rate of change for the first 6 seconds, okay, we're going to use our formula for slope, right? M equals y2 minus y1 over x2 minus x1. So my y2 is 379, and my y1 was 555 over 6 minus 0. Okay, so when I run that through, yeah, I got about negative 29.3 repeating as my rate of change. So that would be in meters per second. So the average rate of change for the first 6 seconds was 29.3 meters per second. Right. So now the instantaneous rate of change at 5 seconds. Again, I don't have a point there, although if we really wanted to, we could probably try to figure it out. But the idea here is I want to draw a tangent line, right? So a line that just barely grazes the surface at 5. Okay, so here's my point, roughly at 5. Okay, and now I'm going to have to draw a line that just brushes past that. So I'm going to come up here, maybe something like that. Again, it's nice with a computer because I can play with this a little bit now and try to line it up. So it's just where I want it. Okay, that looks pretty good. Right, this is just barely brushing past that point. Okay, so here I do have to turn to the graph. Okay, so I'm going to have to find 2 points on this line because they're not points that I already have. So I'm going to have to make a bit of an approximation here. There looks to be a pretty nice point right here. Okay, at about 1.5 and 600. Okay, and for another pretty good point, okay, maybe down here. Okay, at the end of my line segment, I've roughly got 9 and 250. Okay, so those are my 2 points that are on my tangent line, and we'll use that to get the slope. Okay, so for C, I do the same thing now. Okay, so for my slope, I have my y2, which was 250, minus y1, 600, over 9, minus 1.5. Okay. And I'm going to run that through. I'm at about negative 77.7 repeating, so 7, 7, 8, and so on meters per second. Okay. Yeah, so that's our light intro, kind of the visual aspect of finding rates of change using secant lines and tangent lines. Okay, so that is all for this lesson. Okay, there's some practice work going right back to the beginning of the text. Okay, so on page 9, I would like you to work on numbers 2 to 5, 8, 9, and 13. Okay, so have a wonderful rest of the day, and we'll hope to see you next time.